Good afternoon, everyone. Hope you are doing very well. In this lecture, we're going to be discussing about space complexity. So far, we discussed about time complexity. Space complexity is also important to know what it means that how much resources in terms of memory your program is going to take. Let's see what it is. You have seen this diagram we discussed in the very first lecture. In this diagram that we have an input tape and our machine has a control and state registers are there to store the information about in which state our head is. Head can move left, right, or stays at the same location. Now, if you remember, we said in that lecture that we have infinite long tape, but think about for a second, do we have really infinite storage or infinite memory? And in this example, we are using one tape for read, write, and scratch space. Okay? We don't have any more tape. So what it means by space complexity means that we're gonna know the bound, upper bound, for example, how much memory your computational task is gonna take. Before going forward, your textbook defines something called space-bounded computation. What it means that the Turing machine is doing its job, it's deciding based on your input, it's solving the problem. Now it has given a bounded storage, means that in this example, this tape has fixed length. Okay, fixed length. So you have been given certain number of storage cells or certain number of locations on which you can write during the computation, or your program can write, but not infinite, right? So that's the basic idea here, that about space-bounded computation. Okay? Similar to P and NP classes, when we were discussing about time complexity in previous lectures, we discussed about P and NP class, complexity classes. Same way we have P space and NP space complexity classes. Notice here, NP space, P space, okay, denoting respectively for, say, P for all the problems which can be solved in deterministic time, and P, no, I mean, you cannot solve in deterministic time, right? NP problems, NP hard, NP complete. In the same way, you have P space and NP space. We're going to define what is a space. Here is, you can read the definition from your textbook if you want to. The basic idea about this lecture is to introduce you what these terms mean. So, for example, P space you can define for some constant greater than 0 that your space requirement for a string of input length n is n to the power c. Okay. Same way, NP space for all NP problems, you have n space problem size to the power c. What is L? Here, if we take the log of input size, say for example, at least your machine gonna remember one cell on which it is doing computation, right? It may not remember the whole tape, how big is the tape, but at least minimum that one. So we're gonna use, or in your textbook, the L is used in that sense. So for the log n, basically, here it was n to the power c. Here you're talking about the natural logarithm of the n. Same way, and L. Okay. Now let's talk about what we mean by space as n. So technically, how we can define? Let's say S is some function which maps from natural number to natural number, and you have a language L, all possible strings of binary strings 0 and 1. Okay, and you have been given, or your program have been given, there is an input x, okay, belongs to 0 and 1. This is going to be 0. 0 and 1. Now, if there is this information you have given, input x, language L, and we are talking about space. So in the same way, we can define any space later. And you have been given some constant C, and you have a Turing machine, deterministic Turing machine M. Okay. Now, what it means here by space, that your deterministic Turing machine M is solving the problem or deciding, true or false, such that at any given point in time, okay, the total memory or total cells this machine gonna take, or in other words, at any given point in time, non-blank cells will be at most C constant multiplied by S, this S, and have the input, okay, the length. So what we did here, we basically defined a bound for the computation, that your Turing machine at any given point in time will have at most these many cells filled. Okay. In terms of any space, it is very similar, analogous to space. Here you have, instead of deterministic Turing machine, you have, for any space case, non-deterministic Turing machine. Okay. Other things are same. You have language L, input X, constant C, and how much, how many cells, or what is the upper bound, or what at max cell this machine gonna use to compute or to give you the result. And by the way, this is non-deterministic Turing machine. Okay, so that's what we meant. We defined the bound for the space or memory. Now remember, you were defining some sort of bound for time complexity. Say you used to say order of n or order of n square or something, right? So you have upper bound for the time, how much time your algorithm gonna take. In the same way, let's say if there is a function, a space function n, okay, now we can also define the upper bound O of Sn. What it means that that is the upper bound on the memory limit, this particular language L, or any computational task in L gonna take. Okay, O of Sn. So this is a small s and that is big S. So guys, this was very short video to give you an overview about space complexity. It is analogous to time complexity. Okay. Now there are various theorems and proofs, lemma. If you want to know, you can get into detail in your textbook. However, for if you are doing undergraduate, it's just good enough, I guess, for you to know at least what these terms mean. What do we mean by the space requirement for a computational task? Okay. Thank you, and have a wonderful day. Thank you again for subscribing, and those who haven't subscribed, I would recommend you to subscribe the channel so that you can get notification as soon as I upload new lectures. Have a wonderful day.